So we're going to look at an example of nearsighted and farsighted corrective lenses and see how that affects our object and image distances and whatnot. We will start out with a farsighted person with a near point of 100 centimeters. We're going to use some reading glasses that will allow you to read at 25 centimeters, and we want to know what is the power of the lens in order to do that. So essentially, without glasses, we have to hold something way out here to see it, but now we're going to be able to move it up to this point and it will look like it's way out there, and so we will be able to see it when it's way up here. So we're going to use our thin lens equation, 1 over f equals 1 over di plus 1 over do. Focal length is what we're trying to solve for. The object distance, that's where we're going to place the object to be able to see it, and that's 25 centimeters. I'll put that over here first. And then the image distance, it's going to be out here at our near point, which was 100 centimeters. But since that is on this side of the lens, essentially it's a virtual image over here that we're seeing, we need to make sure and have that distance be negative. So 1 over negative 100. And then we just do a bit of algebra and we will get 1 over the focal length is equal to 1 over 33. So that means we need a lens with a focal length of 33 centimeters. But corrective lenses are usually listed as diopters, so we convert this to meters, 0.33 meters, and then we invert that. So the power of the lens is 1 over 0.33, which is going to give us a positive 3.0 diopter lens. That last thing there was a D, not another O. Alright, now let's look at nearsighted. Near point is 12 and far point is 17, so not the greatest range of vision here. And we want to know what power is needed for this person to see a distant object clearly, and then what is that going to do to their near point. So essentially we want objects that are at infinity to appear when we're looking through our lens like they're at 17 centimeters, so that we can actually make an image out of those rays. So again, we will start with our thin lens equation. So 1 over f equals 1 over di plus 1 over do. Again, we're trying to solve for the focal length that we're going to use. We want to have our image distance be 17, so 1 over 17 for that. For objects that are really far away, so 1 over infinity. Oh, I forgot to take into account, we have the lens. We're going to actually consider the fact that the lens is not right on the eye for eyeglasses. We're going to say that it's 2 centimeters out from the eye. So that means we want our image distance to be 15 centimeters because image distances are measured with respect to the lens. So we will change this guy here to 15, which means we're going to get a focal length. Oh, and that is going to be negative again, right? Because it's on this side. So we're going to get a focal length of negative 15 centimeters. And negative tells us it's a diverging lens, and that is all good. So if we want to get this to diopters, negative 0.15 meters, power is going to be 1 over 0.15, which gives us negative 6.7 diopters for the power of that lens. Now, what is that going to do? This is going to help us see faraway objects. What's that going to do with our vision of nearby objects? So objects that were at our near point here at 12 centimeters, they're going to be pushed out a bit because this is a diverging lens. Well, how far out will they be pushed? We can figure that out using our equation one more time. Our focal length is going to be the same as before because we have the same lens. We're not swapping it out. I'm going to go back to centimeters here. The image distance is the distance where we are going to be seeing this thing, and it is measured from the lens, so it's going to be negative 10 because it's a virtual image on this side of the lens. And then we're going to solve for our object distance, which tells us where we're going to place objects such that they appear at our near point. We go ahead and do a proof of algebra, and we get an object distance of 30 centimeters. So before we could see things all the way up to 12 centimeters away. Now we have to hold them out at 30. Now 30 centimeters isn't all that far, so this might not be a big deal. You can still see things. If you're trying to read, holding it at 30 centimeters is probably not a big deal. But again, there's always kind of trade-offs. Now what happens if we're using contact lenses instead of glasses? Well, that's going to change the distance. We're going to assume that we're placing this directly on the eye. So this initial calculation here, we're going to have a 17 there instead of a 15. So our focal length is going to be negative 17 centimeters, which works out to be a power of negative 5.9 diopters. So it changes the power of lens needed a bit, a little bit weaker lens. But if we recalculate this object distance, that works out to be a bit further out. And you'll often find optometrists like glasses. They say they can correct your vision a little bit better with glasses. It's also healthier to let your eyes breathe. I mean, if you do your contacts and take them out every night, then it's okay. But some people sleep in them, and all of those things cause problems. But anyway, here's some calculations for you. All right, that is all. Have a good one.